Hello, this is Deborah Barrett with the Cincinnati State Physics Department, presenting the second in a series of videos on momentum. This video will talk about basic conservation of momentum. You remember that we defined momentum as basically being inertia of motion, and we said that officially momentum is equal to the mass of an object times its velocity. Well, mass means the amount of matter in something, and that doesn't change just because an object's moving along. And the velocity of an object tends to stay constant when an object is moving, or for that matter, if it's not. That's what Newton's first law describes, that tendency of an object to maintain constant velocity. So if you have an object with some momentum, its product of mass times velocity is going to tend to stay the same. And in fact, if there are no outside forces acting on the object, its momentum will stay the same because each part of it tends to stay the same. So we have conservation of momentum for an object, that an object tends to maintain its momentum. The interesting thing is that this is also true when you have a compound object. If you have an object with multiple parts, then they still tend to maintain overall the same mass and velocity as a collection. A good example of this is the slug of shot fired from a shotgun. When you think of that slug of shot as one compound object with multiple parts, all those little shot pellets, they emerge from the barrel of the shotgun with a certain combined mass and velocity. The mass of that slug of shot stays the same as it flies through the air. And if you think of the velocity of that slug, that package of shot pellets overall, that also stays very nearly the same, at least over a fairly short distance. Gravity changes its velocity a little bit, pulling it into a somewhat of a parabolic path. But if you look at it over a fairly short time, you can see that the velocity would stay constant. So the mass times the velocity of that slug of shot would stay the same. Aside from the slightly parabolic trajectory of the Earth's gravitational pull, that's going to be true even if the individual pellets of shot are bouncing off of each other a little bit as they fly through the air. The velocity of that slug of shot overall stays constant. So you have momentum being conserved, that the total momentum of that system of shot pellets stays the same even when you're dealing with a compound object. But if you could fire that shotgun in a place without air resistance and without gravity, then the overall slug of shot would continue its velocity the same as when the shot emerged from the barrel of the gun. That would be true even though the pellets, the individual pellets of shot, bounced off of each other a little bit. The slug might spread a bit, but the overall velocity of that batch of shot pellets would be maintained. And so the mass times the velocity of that slug of shot would stay steady. The idea here is that momentum is conserved even when you have a compound object made up of multiple parts, and even if the parts are interacting with each other, like the pellets in the slug of shot. You still have conservation of momentum if outside forces are not acting on that slug. You can think of the momentum of the compound object as being equal to the sum of the momenta of the parts, so that the momentum of the slug of shot is equal to the sum of the momentum of each of the pellets. That means when we're saying that the total momentum of this compound object stays steady, that means we're saying that the sum of the momenta of the pellets when they first emerge from the barrel of the gun is the same as the sum of the momenta of the pellets as they fly along. This is my preferred way of saying conservation of momentum because it shows explicitly that we're adding up the momentum of any parts of the system first at time 1 and then comparing that total with the total at time 2. You have to keep in mind that when you're doing this, you must take into account the direction of the different objects that make up your compound object. Momentum is a vector quantity with direction, so you have to take that direction into account as you do the analysis. This relationship is going to be valid anytime there are no outside forces acting on your object, and it will actually still be darn near exact even if you have some outside forces that don't balance, as long as those outside forces are much less than any impact forces internal in your object. This relationship is very handy to use when you are trying to analyze the motion changes for more than one object at the same time. And that's when we tend to use it the most heavily. Additional videos in this series will present an example worked out from the text and discuss other issues relating to momentum. Thank you for watching these videos about momentum.